Right? If we go through, what we should be trying to do is find the pieces that show up similarly. Okay, notice that we do have this kind of fan, the isopropyl aspect, in both our starting material and in our product. Okay, so it could just be a straight reacting with itself, a self-aldol. But if we go through and count our carbons, 1, 2, 3, 4, 5 carbons. If we doubled, it would be 10. I get 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's not a self-aldol. This is a crossed aldol. I'm bringing in some kind of carbonyl compound here. Okay? We're cheating a little bit within that context because we just looked at aldol condensation, so that's why we're saying we're doing an aldol. Okay? If we skip that, the other part is now trying to nail down where those pieces are. Okay? So I could have that as my potential structure, but then the issue with that would be, where's the carbonyl? Right? So more than likely, that wasn't the best pair up. The red carbons are probably here, where position 5 in my drawing, oh, believe it or not, I numbered it weird both directions, is position 5 in my starting material. Okay. Position 5 is special because it is the alpha position to our carbonyl. Because it is an alpha position, it has acidic hydrogens. If I remove an acidic hydrogen, I now have a nucleophile. Okay. So as a step 1, if I added some kind of base, I could get a nucleophile that could then react with an electrophile. The electrophile would then need to be the remaining carbons. Okay? So minimally, I know I have 4 carbons. Okay? Where, if my numbering looks reasonable, carbon 4 in my final drawing is the one I need to be electrophilic. Everybody see that? Shall I take that as a yes? I'm just going to take that as a yes. Okay, carbon number 4 needs to be the electrophilic one. And I'm now making the connection between carbon 5 and 4, where 5 is the nucleophile. So 4 needs to be an electrophile. If I just went in and put in a bromine, what becomes problematic? Okay. Sorry, what'd you say? No, you're ignoring, what'd you say? We get a little bit of steric hindrance, but it isn't that bad. We can still get that substitution. Would that get us that product? No, what's missing? We'd be missing the pi bond. Okay. We just did the straight substitution, there's no pi bond in our product. We'd have to run more reactions there, which we could theoretically do, but that's going to scaffold in a whole bunch more steps beyond what we've already got. So how can I get that carbon to be electrophilic and have a pi bond? Well, what if it's a polar pi bond? Now what can happen is my nucleophile can come in, attack, kick that up. We still have an acidic hydrogen. We can do a second elimination, and we've done the aldol condensation to get that product. Okay, or that first product. Make sense? So we have the second reagent. Do we have the first reagent? All I've said is base. Base is not a reagent. Okay, that's a class. Okay. What's the reagent necessary to do this? Well, all I need to do is remove an acidic hydrogen. Well, is there more than one alpha hydrogen in my starting material? Yes, crap. It does matter what base I use. I have to be very particular about which base I use. I want to remove the hydrogen that is most exposed, which would be the least stable enolate. That would be the kinetic product. What base gets me a kinetic enolate? LDA, also known as our stupid strong bases. LDA or NaH. Okay. Both of those would go through and remove that hydrogen, that alpha hydrogen, at the least sterically hindered position. If I use T-butoxide, that's a strong base. That is not a stupid strong base. It would actually form the thermodynamic enolate, which would have the carbons attached to the wrong position. Okay? It would also do just the aldol reaction and not the aldol condensation, because there's only one alpha hydrogen at position 7. Okay? So that gets us to our first intermediate, all that fun structure. So let's clean that all up. We now want to look for that core structure in our product. Hopefully you can see that that core structure is right there. We are reacting at those two positions. How can I name those two positions? Those are the alpha and beta positions. Okay. Between the alpha, beta, and our starting material, that is unsaturated, so I have the potential for running 1,4 additions. Okay. That would put something at the beta position. To get something at the alpha position, I'd have to have a nucleophile. Well, the alpha position is not nucleophilic. Okay. The hydrogen attached to that position is not acidic either, because it's not resonance stabilized. So the alpha position is not reactive right now. The only position that's reactive is the beta position. Okay? Which means the first thing I'm going to try and get on there would be that position, or that ethyl group. Okay? So I need, in my step, 3, I need a CH3CH2. Okay? Because my beta position is an electrophile, that CH3CH2 needs to be a nucleophile. It needs to be negatively charged. What's the problem with a negatively charged carbon? It's hard to get and reactive where? Carbon, yeah. Keep going. Dig me out of this hole. Come on. Where does the negative carbon typically react? With the carbonyl. It typically does a direct 1,2 addition. We want it to do a 1,4 addition. So yes, great. I know I need... What the heck? Oh, sorry. My computer and the iPad aren't talking with each other, right? I know I need a nucleophilic carbon there, but if it's a straight negative carbon, it doesn't do the reaction I want. I want a weak negative carbon. How do I get a weak negative carbon? That's the organocuprates. That's using a Gilman. Okay? The Gilman will now attack at the beta position suite. Okay? We're now advancing somewhere. Okay? That, after that attack, right, if it goes through and attacks, it would put a negative charge on that carbon. Okay? Without fail, everybody in this class went through and said, well, I need to neutralize that carbon. And I would best neutralize a negative by putting on a positive hydrogen. And so you all wrote H+. Okay. What did you do for step 5? Your very next step in step 5 was to remove the very hydrogen you just put on. How about don't put on the hydrogen? Instead of ending the Gilman by adding an acid, end the Gilman by adding another positive atom. That positive atom needs to be that carbon structure, which is 1, 2, 3, 4 carbons. CH3, CH2, CH2, CH2. That last carbon needs to be positively charged. How can I make sure it's positively charged? Put a good leaving group on it. Now you're done. Okay? The people that went through and did those two reagents followed step 3 up with an acid. What did they follow step 4 up with? Or started step 4 with a base and then put on the electrophiles. Okay? So you did counter reactions to each other. You didn't need to do the acid-base parts. So when we're going through and doing synthesis, it's not, oh, Gilman always requires acid. Where are you going? Because you could very well be generating a structure at the end of that first step that you want for the next step. Don't undo the work you've already done. Right? So we could get this done in 3 steps as opposed to the 6 that most people write out. Or 4 steps instead of the 6. Kind of makes sense? Okay. Look for those pieces. At least identify the pieces that need to be changing. Okay. With the carbon-carbon structures, or the carbon-carbon bond formations, these become a lot trickier because sometimes they're self-reacting, in which case you're doubling the number of carbons. Look for that. Look for that doubling number of carbons, because then you're starting with 1 carbon species but somehow getting a whole bunch more. Okay? So look for that, because that probably means you're doing a self-reaction. Okay? Look for it where it's not self-reacting, where you don't get the same number of carbons. That means whatever piece you're adding has to be accounted for somehow in the product that didn't show up in your reactant. By just identifying parts of pieces, you can answer multiple choice questions. Take advantage of that. Okay? Make sense? Okay. So let's now try and whip really, 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 really fast through how many slides? Just under 20 slides. Okay? And I know you might be like, oh my God, it's insane. Ideally, we just cover the content here. The content isn't too bad as far as these reagents go. It isn't horrible. But ideally, you just want to practice it. Whoa, that was faster than I wanted to go. Okay? So chapter 19 is the equivalent of chapter 13. It's a synthesis chapter. Okay? You've now learned a whole lot more reactions. So it's now how do we string those reactions together to do more synthesis. Okay? And so they start to address some kind of things. If we look at, say, reacting those 2 structures, they both have reactive carbons. Those carbons are positively charged, meaning if I want those carbons to react with each other, I need to change one of them, okay? Because I'm not going to get a chemical reaction there. The only reactive species I have are electrophiles. If I could get those 2 carbons to react, what would I need to do? And what would I do it to? I have an alkyl halide, which means if I react that, I should not use a retrosynthesis arrow. If I use a Grignard or add magnesium, that now makes that carbon a nucleophile. It's now negatively charged. Now the negative could attack my carbonyl. So recognizing what I start with 2 electrophiles, make one of them negative. Okay? The process of doing this, or the idea of converting a positive carbon to a negative carbon, or any atom from a positive charge to a negative charge, for some reason gets this stupid German word, which Umpelung pops up every so often. I always wondered where it came from, and our textbook actually explains it. So there you go. That's all it is. We're changing the charge in the atom. That's all you need to know. Okay? So the Grignard is an example of an Umpelung reaction, because you're taking a positive carbon and turning it into a negative carbon. That's it. The Wittig does the same thing. An alkyl halide becomes a negative carbon, that carbonide. Okay? We're just changing the polarity of our structure. So organometallics do this, yada, yada, yada. Okay? The next part is they go through and summarize carbon-carbon bonds. Okay? Anything that forms carbon-carbon bonds. We saw this with the cyanohydrin. We saw it with the alkene. Okay, making an alkene, we did a Wittig reagent. Okay, using an enolate, we could react with another carbonyl and get our aldols. So all they're trying to do is say, realize that we've done all these reactions. Start looking at those summaries to help you memorize them. Okay? How many of you did not realize that there are summaries of reactions in our textbook? Everybody realize that? Really? Oh, okay. So you all looked at the back of the book and were like, oh yeah, these are, oh, okay. Some people shaking their heads, no. Take a look at the back of the book. all of the reactions we've learned to date are summarized, and all the reactions in the whole textbook are summarized at the back, okay? To varying levels. Some of them are organized, you want to make an alkyl halide? These are all the reactions that do it. Some of them are, you're starting with an alkene, these are all of the reactions an alkene can do. So depending on what you're looking for, you can sort through that table to say, that's what I want. Okay? And it's a step better than just listing the reagents, because they also go through and they tell you the section where it's referenced. So you can go back to the chapter and be like, or look at it and be like, that doesn't make any sense. We didn't talk about Wittig or Wittigs. What are Wittigs? 17.7? Oh, yeah, we did talk about that. Why did Mike call it a Wittig? Stupid Germans. Okay? Well, they aren't stupid. They're pretty smart. That's why it gets named after them. Okay? But that's where it's coming from. So you can make reference to that. Start really taking advantage for the rest of the semester, looking at those end of the textbook summaries, okay, for all of your questions. It can simplify a lot of the work that you're trying to go through and do. Okay? So your textbook has some pretty slides there. Okay, the next part is thinking about selective reagents, okay, which, believe it or not, we have talked about. Okay? If I go through to run a reaction with this tosylate structure, okay, if I want a substitution, I can do sodium chloride. That gets me a selective substitution product. If I want to do elimination, I can use a big bulky base. That's going to force a base and not a substitution. So thinking about your reagents, and it's really coming down to nucleophiles versus bases. When you run a reaction, evaluate, this species I want it to be a nucleophile. Oh crap, it can also act as an nucleophiles also act as bases. It can also act as a base. Is there some site in my reaction that could potentially act as an acid? Yeah, okay, that reagent doesn't work. Okay, that is a non-selective reagent. Okay, so we just need to be evaluating what our reagents can do, what directions we can come out of them. Okay, you've already been doing this, you just may not have fully realized that it was important yet. Okay, reduction. Okay, I know that looks like a whole lot of stuff. But this summarizes all of our reduction reagents. Okay? If we had a nonpolar pi bond, we could take hydrogen and pretty much any metal, and we would get rid of the nonpolar pi bond. Okay? Notice, where did I place the hydrogens?
Same side.
On the same side, because in that reaction, the condition for that nonpolar pi bond system up here is that they are a syn addition. So when we look at our products, we might have to consider stereochemistry with those products. We have to remember that. Okay? If we had a triple bond, okay, we could still use hydrogen and our metal catalysts. That would fully reduce. That would get rid of the triple bond entirely. But if I go through, instead of using just a normal metal catalyst, I use a poisoned metal catalyst. Well, poisoned. If you're poisoned, do you function at the same level as you are unpoisoned? No. Usually it means you're dead, right? Okay? Same kind of thing is happening here. The poisoned catalyst prevents the hydrogen from reacting as completely with the nonpolar pi bond. So it only reacts with one of the pi bonds of the triple bond, of the alkyne, and we end up with just the alkene. Again, because it is a metal, you're still doing the syn addition. Okay? Hydrogen with the metal, problem with that is it's not selective. We use it all the time, but it would react with both alkenes and alkynes, so not selective. A poisoned metal is now selective, because what does the poisoned metal react with? Alkynes, not alkenes. So the poisoned catalyst is now a more selective reagent because it reacts with only one functional group. Okay? Another one that we could look at with our triple bonds, this is the trick one that you typically have to memorize, is you take sodium metal and ammonia. Okay? And when we react that with a triple bond, we do a reduction and we end up with the alkene, except the tricky part with that, it's the transalkene. Okay? It's the only reduction that gets a trans or does an anti-addition. Okay? So that's why that one is super important to remember. Okay? Well, the previous two chapters that we were looking at, we started with carbonyls. Well, carbonyls are pi bonds. Okay? Could I use H2 and a poisoned metal to reduce a carbonyl? No, because the poisoned metal reacts with alkynes. Could I use H2 and a normal metal, like platinum, palladium, or nickel? Yeah, that will reduce a carbonyl. Okay? The issue with that is not only does it reduce the carbonyl, it reduces alkenes, alkynes. It reduces everything. Okay? It's not selective. So if I have a structure that has both a carbonyl and nonpolar pi bonds in it, I want to be able to say, I want to reduce that species, but not that one. Okay? That's what Chapter 18 brings in with its reduction reagents. Okay? We get the Wolff-Kitchener, which we talked about. That's nitrogen doing the full substitution, forming effectively the imine. In the presence of the base, we can cleave off nitrogen gas in its entirety, and we end up with no functionality at that carbon. It's a full reduction down to the alkane. Okay? We could also go through and take zinc and mercury in an amalgam. We mix those two metals with each other. In the presence of acid, what else happens? What do we do? Did a full reduction where we completely lose the carbonyl. Okay? Last one. Okay? We take ethane dithiol. Okay? Just two carbons, thiols with the sulfurs. In the presence of acid, react it with the carbonyl, followed by Raney nickel. What happens? Full reduction. You kill it all together. Okay? So those three reagents all do the same thing. Why do I need three reagents to do that? Does anybody notice any differences about those reagents? Or similarities? Because I'm always so subtle. We got any notices yet? Differences in acidic versus basic conditions. Okay? The first one, Wolff-Kitchener, runs under basic conditions. If I have a functional group that is acidic in that compound, what happens? Neutralizes the base. If the base is now neutral, can the Wolff-Kitchener continue? No. So if I want to get rid of that carbonyl, if I have an acidic acid or an acidic structure, that's not going to work. I can't use that reagent. I need a different reagent. I need a reagent that, say, has an acid in it, because now it's not going to change or react with that species, and I can now do the reduction. So depending on what my structure is, I'll navigate between different functional groups or different reagents. Okay? And that's pretty much what the rest of these slides are. Yeah, that's selective. That should have shown up earlier. What? Sorry. Where did all my neat slides go? Oh, you know what? I think it's in a play pause it video. I just remembered that. So I will set up a play pause it video for Monday that goes through and looks at each of those reagents. Okay, these three reagents are redox reagents. Okay, I'll put that up so that you can recognize what's going on with that, and we can talk about those in a little bit more depth on Monday if you have questions. Okay, ultimately, you need to know that those reagents do the reduction, and they have slightly different conditions for them. Right? So recognizing the key differences and similarities between them is going to be the important part.
What's the differences between the acids, the heat?
If we look between the acid ones, we have heat. We also have that thiol. Okay? What is the thiol acting as in this case? Where's sulfur on the periodic table? Right below oxygen. So that structure could just as easily have been something kind of like this, right? What is the oxygen or the sulfur potentially acting as? A what? A nucleophile reacting with what?
Carbonyl.
The electrophilic carbonyl. To make, if they were oxygens, it would be making not an alcohol.
No.
The oxygen comes in and attacks. We'd have an OH, and then we'd have an O carbon. We'd have an alcohol and an ether in the same structure. We'd have the hemiacetal. There's a second OH. It can attack a second time. We'd end up with an acetal. We can't do it with oxygens. It has to be sulfur, because sulfur does some sneaky backhanded chemistry, okay, that allows the full reduction later on. So what's the big difference between the zinc amalgam and the sulfur reduction? The sulfur reduction, that's a nucleophile. Up here, no nucleophile. So if I have an electrophilic site somewhere in my structure, this reaction, bad idea, because the sulfur could attack that electrophilic site. Right? So there is a subtle difference there. It's not just acids and bases, it's also recognizing the nucleophilic characteristics of those reagents. Okay? So this one is nucleophilic and acidic. This one is officially nucleophilic too, and basic. And this one's just acidic and does some goofy chemistry. That's what I thought I had as a slide in here. It must just be in the video, because it does some really neat chemistry. Okay? So recognizing those subtle differences, when we look at a structure, we have to say, does it have an electrophile in it other than the carbonyl? Then I can't reduce the carbonyl using the dithiol. I can't reduce it using the Wolff-Kitchener, because both of those have nucleophiles in them that would react with other electrophiles other than the carbonyl. So I would have to move to the zinc amalgam. Kind of makes sense? So recognizing the reactivity of those reagents can help you predict when and why, when not to use them. Okay? So other selective reagents, we saw this. Okay? LDA and T-butoxide both act as bases. Okay? They're both doing a base reaction, yet when we start with this ketone, what's the issue with the ketone? It is unsymmetric, which means the bases then have a selectivity for one side or the other. LDA selectively went for the kinetic product, which means we get the substitution happening on the less substituted site. T-butoxide forms the thermodynamic enolate, which means I get the substitution happening at the more substituted position. So we've seen this selectivity, or this concept of selectivity before, we just haven't fully directly addressed it. Okay? I don't want to stress about the synthesis right now. We can talk about that maybe on Monday. The last part that I want to get into is our reactions of our alcohols and the oxidations. So what we've done is said we've got a carbonyl. How do these carbonyls work? Okay, they're electrophiles. Okay, they have acidic hydrogens. So I've looked at how I can get the carbonyl to do stuff. But how do I make it? Okay, we haven't really talked about how we make a carbonyl. Okay, the synthesis of a carbonyl is typically going to come from an alcohol, and we're now increasing the amount of bonds to oxygen. So it's an oxidation reaction. Okay, so if we have oxidizing agents, we've got the reagent to functionalize this, or to generate our carbonyls. Okay? As far as you're concerned, there are only two oxidizing agents, okay, for the lecture. Okay? And that's kind of a weird thing to say, because I would make the argument there's actually only one. We have one oxidizing agent, and it is chromic acid. Okay? The fun thing with chromic acid is that I could just write chromic acid. That would be the same thing as saying H2CrO4. That's the same thing as saying K2Cr2O7 in the presence of H2SO4 and heat. It's also the same thing as the Jones reagent. There's a variety of ways to say chromic acid. Okay? So if you see chromium and any form of acid, it's chromic acid. That's the best way to do it. Okay? Chromic or chromium is a wicked strong oxidizing agent. So it will oxidize the crap out of anything it touches, as long as there's hydrogens to also remove. Okay? So if we take a look at a primary alcohol, I want to be able to oxidize that carbon by increasing the bonds to oxygen. Okay? Are there hydrogens to remove from that carbon? Yeah, there's 2 hydrogens. So what does chromium go through and do? Go away hydrogen, I'm replacing you with oxygen. Okay? We now have too many oxygens at that position, so we'll condense the oxygens down or simplify that. Still 3 bonds to oxygen, but there's only 2 oxygens. So if I oxidize a primary alcohol, I will end up with a carboxylic acid. 3 bonds to oxygen. Every hydrogen is replaced with oxygen. Okay? What if I have a secondary alcohol? Well, how many hydrogens are there available to remove? Just 1. So I will go through and replace that hydrogen with an alcohol. What functional group did I just draw? A hydrate. And what do we know about the hydrates? They are unstable and very quickly revert to the ketone. Okay? The hydrate is unstable and will revert to that carbonyl compound. Same kind of thing happened with our primary alcohol. Okay? We had those 2 hydrogens. We removed the 2 hydrogens and replaced them with oxygens. What we've got there is like an uber hydrate, if you want to call it that. Okay? That's unstable, and it reverts to the carbonyl. Okay? So all we're doing is replacing hydrogen with oxygen. This is what chromium does. It just oxidizes the crap out of whatever it sees, and we go to the full carbonyl. Notice I don't have any tertiary alcohols on my list. Why not? There's no hydrogen on a tertiary alcohol, which means what happens when I add chromic acid to it? Nothing. Absolutely nothing. So we're only looking at the primary alcohols and the secondary alcohols. Okay? So that's chromic acid. It'll take your alcohols down to either ketones or carboxylic acids. Okay? Then there's a whole other section to this, a bottom one. And I said really there's only one oxidizing agent, chromic acid. Okay? But this one is pyridinium chlorochromate, also known as PCC. Okay? PCC, okay, one of those C's stood for chromate. So guess what my oxidizing agent is? The exact same thing as chromic acid. It is chromium. It's still doing the oxidation. Okay? But what is bizarre or different about PCC in comparison to just straight chromic acid? It's milder. The secondary alcohol does the exact same thing. What did the primary alcohol do? It's not just that it takes off one, because then if I drew an aldehyde, well, it still has a hydrogen. Would it take off one then? No, it's not that it takes off one, is it will only do one oxidation. Right? It stops at the aldehyde. PCC is a milder oxidizing agent, and it cannot oxidize it as far. It stops at the carbonyl. Okay? I like to refer to PCC as politically correct chromic acid because politically correct humor is usually a milder form of humor. Okay? PCC is politically correct chromic acid. It's milder. It doesn't quite do the same level of oxidation as straight chromic acid down in the depths of the internet. Okay? Dark, bad humor. Okay? Like every other organic constructor, it's PCC. Okay? So why do we get this difference? Okay? Well, the difference between PCC and chromic acid really boils down to these two structures. The solvent for PCC or for chromic acid is water. The solvent for PCC is technically pyridine. Okay? It is still chromic acid. It is still acidic. But pyridine has that nitrogen, which is slightly basic and can accept a hydrogen. That's why we call it pyridinium, is because there's that ion floating around. So it's really the solvent difference between water and pyridine. Okay? And that's it. That's the only difference between those two mechanisms, or those two reagents, is that we no longer have water, we have pyridine. And that all of a sudden shuts down further oxidation. Right? And that does seem slightly odd, but it comes back to the characteristics of water and pyridine. Both of them will go through a sequence of steps, and if we look at kind of an approximative step, your alcohol acts as a nucleophile, attacks the chromium. We end up losing a water from that structure. We lose the hydrogen, and we end up with our chromic ester, okay, or chromate ester. That structure falls apart to give us our carbonyl. How? A base somewhere in solution, like water, comes along, removes that hydrogen, forms the carbonyl, and we can now eject the chromate structure, our CrO3. And we end up with the aldehyde. Both mechanisms do this. Okay? So now why the difference between them? Okay? In the presence of water and a carbonyl, what happens? Water is a nucleophile, the carbonyl is an electrophile. I can form a hydrate. The hydrate has what functional groups? Alcohols. The alcohols are nucleophilic. Those nucleophilic alcohols can attack chromium a second time. And we reform our chromate ester. If there's still a hydrogen remaining within our structure, what can happen? Our base can come along, remove that hydrogen, reform the carbonyl, and kick out our chromate structure. So the presence of water is what allows for that full oxidation. Because if we look at the product of that now, we now have our carboxylic acid. But if we were in pyridine, we'd have nitrogen instead of the oxygen. Well, nitrogen is technically a better nucleophile, but is pyridine as good of a nucleophile? No, because it's bulky. We're in an acidic environment. It's protonated. Everything about that nitrogen is non-nucleophilic, which means as soon as I form the carbonyl, there's now no nucleophile to attack. I can't form the alcohol. No alcohol means no nucleophile, which means no oxidation. Okay? You might say, well, really? Yeah, really. If we take PCC, and instead of doing PCC with a primary alcohol and just pyridine, we take that primary alcohol, PCC, and I add water to it. Guess what I get as a product? The carboxylic acid. Okay? By removal of the water, I prevent the further oxidation. Okay? It's all about the presence of water. Chromic acid has water, PCC does not. Okay? Our oxidation summary summarizes all of those. Okay? The R's, that very first one, I'm saying one R is a carbon, the other two are hydrogens. What kind of an alcohol am I looking at? A primary alcohol. The next one would be a secondary. The next one would be a tertiary. Okay? Kind of makes sense? So I'm trying to spider that out. Notice that even for the tertiary, I'm showing a product. What is that product? Same thing as your starting material. That is because typically you'll see them show that. They'll be like, what's the product of this? And you'll be like, well, there's no reaction. But I have 4 structures shown. Oh, it must have done something then. I'm just going to say it oxidized because I know that region oxidized. Whoa! Hold your horses. It can't oxidize. Pick the structure that's the same. Okay? Sometimes you'll see it shown as no reaction, but that's typically rare. Okay? With that, I will stop.